problems, come by and see me, because I do know that there's a lot of times teacher explains stuff to you and you have no idea what they're talking about. So, and business calculus is not that difficult, especially when you don't have trig. I mean, you don't have any trig in it. So all it is derivatives and antiderivatives. And where you're going to have the biggest problem is in the first section on limits. That's where the biggest confusion is going to come. If you have a teacher that explains limits real good, you'll be okay. If you have a teacher that just assumes that you know what limits are, it's going to be a rough first unit. So come by my office if you need me. You know where my office is. Is it in there?
Yeah.
What does it say about it?
It's not good.
Oh crap. Well then, plan to come see me. I don't mind teaching calculus. I love calculus. I just don't like 130. In my opinion, they should teach college algebra, Calc 1, 2, and 3. That's it.
No problem.
No problems in stat. No, they should just teach those classes. If you can master those classes, trig, college algebra, college trig, and the 3 calculuses, you don't have to go to 3, but you know, the 1, 2, and 3 based on your major. You can apply pretty much anything to business, or you don't need all these underwater firefighting maths. I don't think you do, in my opinion. What did I say we were going to go over? 5.1. There we go. Okay.
Did you teach for 1 and 9 next semester?
I don't think so. I don't think so.
And some of those.
Let's see, exponentials. Let's see what they're going to do. Yep, they're doing that. Where x is the variable, we haven't covered that yet, so we'll go over that. Let me make this smaller. I can't stand when I can't see the whole page. There we go. That. Yep. Okay. Now, as far as graphing exponential functions, you ain't got to do it by hand. You still got to do the vertical and horizontal shifts. You know, if they asked you what is a vertical, you know, if they give you a, you know, y is equal to 4 to the x power plus 4, you know that plus 4 is a vertical shift. If they give you x plus 4 raised to the x power or something like that plus 4, you know it's got a horizontal shift. But I'm not really too concerned with that, because most of the time they don't give you that. But what I do want to show you before we get into growth and decay is I just wanted to show you a couple of examples of some of the ones that you might go into. Right now I don't see one that they are actually y to the 2x. You could graph that one. Yeah, go ahead and do y to the 2x. Well, if you don't have a calculator, I'll do it for you. This is how you type it in. Graph y is equal to 2 to the x power, and you hit graph, and there it is. Now, what do you notice about this graph? Tell me anything you notice about it. I'm sorry, what? No x-intercepts. It converges on the x-axis, yes. What would you say?
I said, how do you do it again?
Graph, hit graph, and then 2, caret symbol, x, and hit graph. Or y is equal. Hit y is equal, and then 2, caret symbol, x, and then hit graph. And you'll get this function right here. I'm going to zoom in just to make it a little bit clearer. There. It's increasing. right? What else? What else can you tell me about it? It has a y-intercept, but what else? Tell me how it starts and ends.
Kind of goes along the x-axis.
Okay, what about that? What is it doing?
Branching off from the x-axis.
No, converging onto the x-axis, but what's it doing? As you read from left to right, what is that curve doing?
Going up, up.
Does it go up drastically at the beginning? It's very what? Gradual. And then all of a sudden, what does it do? It takes off blank. What's the old saying? It grows blank. Exponentially. Good. Give your parents an A+. All right? Anytime you hear something growing at a fast rate, you should have heard that thing's growing exponentially. And that's why. When a function is raised to an exponent, you're going to either see a radical change increase or a radical change what? Decrease. This is your increasing graph. This is associated with a lot of business models, a lot of savings models, a lot of production models. Anything having to do with something increasing, this is your model. This is your parent graph. Y is equal to 1 to the x. 1 to the x really doesn't work very well, so they start off with 2 to the x. 2 to the x is your kind of parent graph. Now, if you had 2 to the x plus 4, you'd have a vertical shift of 4, and your x-axis would be at 4, 1, 2, 3, 4, and you'd have the same graph, only it would be up here. Okay, so the vertical and horizontal shifts still apply, but you're not going to see a lot of them. And yes, you're going to rely on your graph. You're going to rely on your calculator a good bit in this section, especially if I asked you to graph or identify an exponential. I'm not going to ask you to graph it by hand because it's a pain in the butt. All right? So y'all good with that? So you'll have one question on the test that says graph. So you can do it on the calculator. I'm just kidding. All right? I'll give you 2 or 3 so you can at least make a 30 on the test. All right? And that's what this just says. It grows exponentially. You're used to seeing something like this that grows gradually, or something like a parabola. That's what y'all are used to seeing. But now you're seeing something that goes, and it just all of a sudden turns and then takes off. Trying to think of a real world application, but I'll think of it in a minute. There it is right there. Graph of exponential functions. This is growth. Y is equal to b to the x. And they should be talking about growth somewhere in here. There's your horizontal asymptote, x-axis. Your domain, all real numbers. Your range, all real numbers. But they have to be greater than 0 because you're not going to get a negative number for y on these. Your y-intercept is always going to be 1 unless it has a vertical shift. Here's where you see your vertical and horizontal shifts right here. This has got a vertical shift of 2 and a horizontal shift of 4 to the right. And they probably show that on the next page. Yep. So, you can what you've learned with the parabolas, you can apply here. What did I say? Well, let's go back and look. Which one is attached to the x? Which on B? Which one is attached to the x? On B, right here. Look. Which one is attached to the x? The 4. So what is that? Anything attached to the x is a what shift? Horizontal shift. And it's always opposites. This is negative, so you got to go 4 right. And what is this? What's the 2? You can actually make this 3 to the x minus 4 plus 2. What would the plus 2 be? It's off by itself. What kind of shift? Vertical shift. So 2 up and 4 to the right. So let's look at B. B. 2 up and 1, 2, 3, 4 to the right. Okay? Now, you don't have to worry about that too much because you can always plug it in your calculator and put it against the parent graph. I'm not going to spend an hour showing you how to do that in your calculator. You should be able to graph those. And if you can graph these 3 examples on your calculator, you're doing good. Because that's not what I'm going to test you on. All right? Now, you might have 2 or 3 of these on the test, but that's it. Anything having to do with income, like right here, this is an example of interest generated. It says total personal income in the United States for selected years from 1960 and projected to 20 can be modeled by y is equal to b or a b to the x power. All right, with x equal to the number of years after 1960. So at 1960, what is x? 0. And 0 times, 0, 1.07 raised to the 0 power is what? Huh? 1. Anything raised to the 0 power is 1. And 1 times 492 is 492. So at 0, you're starting at 492. So that's where you're starting. So your graph is going to start at 492. It's going to go up like this. Okay? What does the model predict the total U.S. personal income to be in 2014? Well, what's 2014 minus 60? 1960. What does that come out to be? Well, 60 plus 40 is 2,000, and then 14, so that'd be 54, right? So you plug in 54 right there. 1.07 times to the 54th power, still going to be around 1, times 492.4, and that gives you whatever number that comes out to be, blah, blah, blah. So, you know, plug and what? Plug and chug. I'm not going to spend a lot of time teaching you that. All right? And you can graph that and look at the table and get your numbers there if you want to.
So basically it's plugging into the exponent?
Mm-hmm. Because x is the exponent. Yeah, just get on out of here. Leave. All right, right here. Write down the exponential decay. And that's y is equal to a times b to the kx. Write that down, because this is decay, half-life, battery life, nuclear life. A lot of your radioactive material is done with a decay formula. Battery life, plutonium, carbon dating, all of that is done with this model right here. Now, in case y'all's in business, you're going to see a lot of sales. Because no matter what you're selling, you could be selling the hottest thing on the market. But what will it eventually do? People are going to get what? Tired of it. Anything you sell is going to fall with this model. What do you mean above the B? A, B to the KX. Does anybody still have a Rubik's Cube? Nope. What else? What else? Oh, well, you know, here lately in the late 90s and early 2000s, it was get a Harley and get a tattoo. Even those are starting to plateau out. Fads do this. Okay? But no matter what you make, if you invent something, people will go crazy over it, and then you will see a decline because people get tired of it. Make sure you know how to graph it. Make sure you know how to read it. Simple as that. Huh? When this right here, B has to be greater than 1. A has to be greater than 0. And K has to be less than 0. They're giving you parameters. You don't need to worry about that because most of the time you just plug this in the graphing calculator and read it. But you need to know decay and growth. Here you go. You need to make a note about E. E is equal to 2.7182, blah, 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 blah. It's just like pi. It's one of those numbers that you need to be aware of. You don't have to memorize it, but you need to be aware of it, especially in banking and business. Because continual interest is done with E. You don't even put in a rate, you just use E. And a lot of banks use continuing interest. A lot of economics uses continuing interest using E. Just make sure you know it's around 2.7. You can use the calculator will put it in there. And you'll see probably on the next page where you're going to use E. Right there. Continual interest. S is equal to principal times E to the RT. R being the rate and T being the time that you keep the money in the bank. You might want to write that formula down because that is a formula that is nice to know. S is equal to P, which is the principal, what money you're putting in the bank. E is blah, 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 that number, a constant. And R is the rate, the interest rate. And then T is the number of years that you keep the money invested. Now they can be using that as growth of an investment also. It can also be used as continual interest instead of compounded interest. If $10,000 is invested for 15 years at 10%, blah, 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 blah. So that's going to be 10,000 times E to the 15 times 0.10. Well, what's 10% of 15? 1.5, Hubert. That's right, class.
Wait.
So that would be 10,000 raised to the 1e to the 1.5 power. Do y'all not have books? We're on page 320. Okay? And what does that come out to be? 44,000. So at the end of 15 years, how much money have you made? 34,000. R times T. R is the rate. T is the number of years that you keep it in the bank or the investment. Rate is 10%, so that'd be 0.1 times 15, and 10% of 15 is 1.5, so that would be 10,000 times E to the 1.5 power. And you would type that in just like so. 10,000 times E, which is second. Always lose it. There it is. Natural log 1.5. Enter. And there's your answer. $44,816. So you made $34,816 minus 10,000 equals divided by how many years? So you made $34,000 a year. That's not too bad. Oh, wait a minute. I didn't do that right. I was supposed to divide by... Why did I divide by 153?
Subtract. 150.
No, that's not right. It's not right. Plus, that's times, plus 153. Is that my original 34,000 divided by 12? Right? Comes out to be $2,000 or almost $3,000 a year.
12 or 15? 12 or 15?
12. There's 12 months in a year, right? Oh, 15. I'm sorry. Just forget it. You don't have to do that. I was just don't even worry about it.
When you did 10,000 times e to the 1.5, did you get 44,000 something? And then what did you do?
That's it. Just the answer.
But you're thinking,
I was doing something that was just, don't worry about it. You don't have to do it. Okay, I was just playing with the calculator. Okay, that's good. Now, make sure you know how to do that. Make sure you can do a compound interest. It's actually, okay, compounded continuously. Continual interest or compounded continuously, either one. That's the same thing. Because that's the test question on the test. So right now, you've got, make sure you can identify a growth graph and a decay graph, and make sure you can work an interest problem. That's not very difficult. Carbon dating, you can make sure you know it, but I'm probably not going to ask you a carbon dating since none of you are going into the sciences. But carbon dating is given by this formula, which is a derivation of your other formula. Y over y sub 0 is equal to E to the negative 0.0001. There's 3 zeros. 2097 times T. And T is time. And I would try to blow that up, but if I blew it up, it would get even blurrier. No, it won't. There you go.
Y over y.
Y sub 0, your initial Y. They'll tell you what everything is. All you have to do is plug it in. Now, you could derive it, and you get Y is equal to Y sub 0 times E to the blah, blah, blah. So this is your formula that you're going to see most. And just take that F of T out and put a Y there. I don't know why they have to make things difficult. So here we go. If the original amount, original means Y sub 0, okay? If the original amount of carbon-14 present in an artifact is 100 grams, so 100 is what? Y sub 0. Anytime you have a variable sub 0, V sub 0, what does V sub 0 mean? Anybody know? What do you think V stands for in science?
Is it something specific?
Yeah, I'm asking y'all. What do y'all think it means? It's not victory.
Velocity.
Wait,
Velocity. Good.
I thought you said the.
V is in Victor. I said Victor.
It still sounds like you're saying the.
V is in Victor.
Now it sounds like you're saying the.
Okay. V is velocity. So what would velocity sub 0 or V sub 0 mean? Your initial velocity. Anything with sub 0 on it means you're starting off whatever. Your initial whatever. So in this case, your initial carbon is 100 grams. So that's Y sub 0. And it'll say the original amount. And then what is T? 2000. Plug and chug. And that's what they did right here. So far, you got 4 questions on your test to go over. And we're going to do some in class, don't worry. And that's it. That's 5.1. We're going to get into logarithms in a minute. And that's where most of your test is going to come from. Make this smaller because I can't see the whole page. There we go. Logarithms. So we're going to talk about that now. And that's where most of your test is going to come from. Y'all remember back in algebra when you learned your exponential laws? Let's go over them just so you remember. The first one is called the product rule. I'm sorry. Yeah, product rule. And that's when you have the same base and you're multiplying, thus product. X to the A, or n, times x to the n is equal to x to the what? M plus n, meaning that if you have the same base and you are multiplying the two terms and they have the same base, what do you do with the exponents? Add the exponents. That's the product rule of exponents. 2, the quotient rule. What does the quotient rule say? If you have, that's supposed to be an A, isn't it? I don't know. If you have the same base and you're dividing exponents, what do you do with the exponent? Or dividing the terms, what do you do with the exponents? Subtract them. That's called the quotient rule. Is it spelled I-E-N-T or A-N-T? I think it's E-N-T, but I'm not sure. X to the M minus N. And then there's the power rule, used a good bit. If I have an exponent raised to another exponent, what do I do with the exponents? Multiply. So this one is addition, this one is subtraction, and this one is what? Multiplication. Pretty simple. Well, what's the other one? Well, the last one, or the last two, number 4, is called the inverse rule. Does anybody know why we use the inverse rule? Might want to take a stab at it. It's really not mathematical. To make it look pretty, because the inverse rule does away with what? Negative what? Negative exponents. It does away with negative exponents. If I have a negative exponent, x is equal to the negative n power, that's over what? 1. What do I do to get the exponent to be positive? Flip it, Hubert. That's right, class. And vice versa. If I have 1 over x to the negative n, what do I do to get the variable positive? Flip it, Hubert. That's right, class. I'm kidding. So why do we use the inverse rule? To make the problem what? Prettier. There is no mathematical value to the inverse rule. You just make it look better. Kind of like putting lipstick on pig. You put a lipstick on pig, it makes it look a little bit better, but still what? Still a pig. Alright, 5. Another one. The inverse power rule. The inverse power rule is another one. I can't spell. I better change that. What is that? Power rule. And the inverse power rule says if I have two terms and I'm dividing them, x to the n over y to the m raised to the negative w power. In other words, if I have a negative exponent on the outside, what can I do to make that w positive? Flip the inside parenthesis. And that'll give me y to the m over x to the n raised to the w power. Again, it's only to make things look what? Better or prettier. So the last two I'm really not concerned with, but the first three you should know. Now, if you need to know it for this chapter, no. Well, then why am I showing it to you? Because a logarithm is a glorified exponent. Okay? And if you know the exponential rules back in algebra, the logarithmic rules aren't that difficult. Alright, so let's go into the logarithmic rules. This is not for tests. This is for you to remember because you're going to see a similarity, especially with these three, you're going to see a similarity. Okay, now let me show them to you. And I just say log, L-O-G. I'm an L-O-G teacher. I don't use natural log very much. Usually you have teachers that either like L-O-G or natural log. What are those two things? Well, let me go ahead and explain that to you. There's two bases with logs. Two bases with LOGs. There is log base 10, which is log, L-O-G. And then there is log base what? No, you're close. E. And that's natural log. These are the only two things in your calculator that can be calculated. Those two things right there. Except they don't put this on the calculator. What do they put? This. So look on your calculator. And usually these two, natural log and LOG, are usually in the same vicinity. Doesn't matter which one you use. Doesn't matter. So, here are some of the logarithmic rules. Log base A of, I'm going to put the, let's just assume if there's nothing there, if there's nothing here, what's it assumed to be? Assumed to be a 10, okay? Log of A plus log of B is equal to log A times B. So what rule is that? Go back to the exponential laws. No, the other B. Product rule. So this is the product rule of logarithm. What's this? What's this? Okay, and that's the product rule. Product has to do with multiplication. What's this one? What's that one? What's that dot mean?
It's a multiplication dot.
Okay, and what's this one? Multiplication. So product rule works for both. You see the similarity? thing in the world to sit on this thing is the pinwheel. So do you see the similarities with the product rule? Multiplication means you're going to add. Add means you're going to multiply. Same thing with your exponential rule. So that's number one. There is no 5 or 6. It's either 4 or 7. All right, so that's your first rule. What do you think the second rule of logarithm is called? The quotient rule. Log of A minus log of B is equal to log of what? A divided by B. And that is your quotient rule. See the similarity? Now, these can also be done with natural logs. In other words, I'm going to put up here, I'll tell you what. You don't have to on your, you don't have to, but I'm going to take this one, I'm going to spread it out a little bit. It's not going to let me, so. What I'll do is this. I'll take this and I'll make it a little bit smaller, if that's okay with y'all. There, how's that? Is that okay? And then over here, I'll do in red. Oh, I think I need to quit. Natural log of A plus the natural log of B is equal to the natural log, I'm running out of room again, of A times B. The natural log of A minus the natural log of B is equal to the natural log of A divided by B. So do you see that the LOG and the natural log principles work together? It doesn't matter which one you decide to use. Everybody with me? What do you think the third one's called? Power rule. Now this one's a little bit different from the exponent, but it has to do with the exponent. This one says log of A, I'm going to make a lowercase a because I'm putting the exponent right here, of x is equal to x times the log of A. What did I do? I brought the exponent out front. And I'm going to draw a little like this right here. That's what I did. And I can do it the other way. I can go, if I have two LOG of 3, then I can make that log base 3, log of 3 to the second power, which is log of what? 9. See, I can go both ways. I can go this way, from here to here, or I can go this way from here to here. Same thing with these. I can go from here to here, or I can go from here to here, I can go from here to here, or I can go from here to here. Is natural log the same? Yes. If I did natural log, it would be natural log of A to the x power is equal to x natural log of A. All of them work with natural log or LOG. Now you have to memorize these just like you had to memorize the exponential rules back in algebra. Okay? And it's real easy to remember. Why? Why is it easy to remember? It's the same thing. See? A plus B is equal to A times B. Go back. A plus B is equal to A times B. The same thing over and over. Now, believe it or not, there's only one other rule you need to remember. And this is called change base formula. Change base formula. Now, what did I tell you was the only two bases that you can calculate? Okay, so this is the only thing you can use in your calculator. Log base 10, which is LOG, or log base E, which is what? Natural log. These are the only two that you can calculate mathematically. Well, what happens when they give you a base of 8? Well, you have to change it. And the way that the change base formula reads is that I have log base, what's a weird letter? Give me a weird letter. Q. Log base Q of, give me another weird letter. Z. Okay? And the reason I gave you weird letters is because when you see log base 8 or log base 5, a little flag should go up. This is weird. I cannot calculate. You put log base 5 in your calculator, and your calculator will blow up. It won't blow up. You can't do it. So, the way that you change is you take the Q, and it goes on top. What's it on right now? Where's the Q right now? It's on the bottom, right? So, think of it as opposite. Goes on the top. Log of Q over log of what? Z. And what is the LOG if nothing is there? What's this assumed to be? Log of 10, which log base 10, which is LOG. So now I can do this problem in your calculator by doing log of Q over log of Z. Can you do it with natural log? Yes. Natural log. Well, natural log is log base E. So let me just show you that, doing that. And that's the way I do it because it's less confusing. I don't like to use LN. I like to use log base E because when I see log base E, I know I need to do a change base formula. Okay? If they give me something weird. So if they give me log, well, let's just do log base E of 4. Well, then I automatically know that I can do the natural log of 4, or I can do log of E over what? Log of 4. That's why I like to deal with log, LOG. I do not like to deal with natural log. And that's just me. It's a personal preference. I can deal with it. If somebody gives me a question, I can deal with it, but I'd rather deal with LOG because of this. I know that these two are that, and I don't have to worry about anything when I got those two bases because I can convert anything. That's just me. Now, on a scale from 1 to 10, how important is this change base formula? It's about an 8.5 for the test, so make sure you know how to use it. It's real simple. It's not hard at all. None of these problems are hard. Mathematically, they're not hard. The last two chapters, the last 2 units y'all had was hard mathematically. This is not hard. This is nothing but, if you like puzzles or Rubik's Cubes or puzzles or whatever, that's what this is. Except for this is just change it and put it in your calculator and it spits out a number. Somebody look in your book and tell me where we are. You got a book? Oh, I'll look. Don't worry. I don't want y'all to have to work. You brought the wrong book. Oh, that's even better, loser.
I stopped bringing my book. How could you bring the wrong book?
He don't care about this class. He don't care. I saw him walking out the road. Yeah, I saw him walking outside a while ago. He was looking for a place to smoke his reefer.
I'm going to sell it actually.
Yeah. All right, there's one other thing I want to show you. And this is a property. It's right here. So far I've shown you 3, 4, 5 things that make up 80% of the test. All right? That's the product rule, power rule, quotient rule, change-based formula, and this. The definition of logarithm. This is how you rewrite a logarithm as an exponent. Y, let me just write it here. Y is equal to log base b of x. That's what this says. That can be changed into this. And I'm going to put a yield marker here, meaning that you can write this as x is equal to b to the y. So if I give you y is equal to log base 2 of x, you can rewrite that as x is equal to 2 to the y. And sometimes there'll be numbers all in here, and you just have to convert it to this. And we'll go over some examples of that too. Now let me show you an example, because if I show you an example of this right quick, you may start to see what a logarithm actually is. A logarithm is a glorified what? Exponent. Exponent on steroids. Exponent with makeup. However you want to symbolize it, picture, however you want to picture it, that's what it is. It's an exponent with a Cadillac. It's an exponent with a Mercedes. It's an exponent with diamonds. It's a glorified exponent. It's a step above an exponent. Now, let's take a look at this one right here. X is equal to 3 to the y. Let's look at that one. X is equal to 3 to the y. X is equal to 3 to the y power. Now, I could graph this, and let's just see what kind of graph. We can't graph it on the graphic calculator. You might can. I don't know how. If you know how, tell me and let me know. But this is supposed to be y right here. Now, we can find the inverse of it. The inverse would be what? Y is equal to what? 3 to the what? X power, right? That's the inverse. So let's look at the inverse. And I just want you don't have to write anything. I just want you to look up here and just think why I'm doing it. That's all I want you to do. So here is, this is y to the 3x, so it's going to be a little bit steeper than y to the 2 to the x. So it's going to look something, I don't know, like this maybe. So what would the inverse look like? Like what? Would it be like this? Or would it be like this? Probably something like this. Okay. Okay, does that make sense? Alright, now, let's take a look at this is written as a what? It's written as an exponent, but we can write it as logarithm, can't we? Oops, sorry. Right here. So I'm going to take this, and I'm going to copy it. And I'm going to paste it on my handy dandy white sheet. I hate this little button. It never works. Paste. There we go. Don't you do that. Oh. did a CAD thing there. Okay. So which one do we have right here? Do we have the right hand side or the left hand side? The right hand side, yeah. We got the right hand side. So this is equal to x. What's 3 equal to? B. And what's y equal to? Y. Alright, now plug and chug into this. So y is equal to log base what? Log base 3. Where's my 3? Oh, log base 3 of what? X. Now we can't do this in the calculator. Why? Log base 3. But now we know the change base formula. Y is equal to log of what? 3 over log of what? Now graph that. Now we put in our handy dandy calculator. And let's go ahead and graph y to the 3x too. I can't graph the other one, but y to the 3x like that. And then I'll do the other one in dark color. I wish I could graph the other one. Y'all need to see how to graph the other one. X is equal to 3 to the y. I think there's a way of doing it. And that's equal to parentheses log of 3 divided by, I better put that in parentheses too, divided by parentheses log of x. Somebody needs to Google that. Let's Google that right quick. Because I've never tried to. I don't know. How to graph. I think you change the settings from parametric to, from quadratic to parametric or something like that. How to graph, I done forgot it. What is it? X is equal to what? No, 2 to the y or what? What is it? The original.
3 to the y.
3 to the y on TI 83. No. What are these called again? Exponential. What's the 5.1 called? The title of it. Y'all don't have your books. I forgot. I'm sorry. Look at the syllabus.
Exponential functions.
Okay, exponential function. How to graph exponential functions. And it's going to say, just type in y is equal to x. That's what it's going to say, and I don't mean to do that. There's a way you can do it. I just haven't done it in since Clemson. So y'all need to see, that's exponential decay. I know how to graph that. But how do you graph the inverse? Well, that'd be something good for y'all to inverse exponential function. Are you from England?
Yes.
I just now picked that up because you don't talk very much. Does it rain over there all the time like the Brits told us? We would trade with the Brits over in Saudi Arabia. We'd catch up with them and they'd eat like kings. We'd be eating MREs with sand in it. They'd be eating like buffet like Morrison's or something. We would trade them our K-bars, we would trade them our MREs, we'd trade them our camis with USMC because they're crazy about the British Marines over there are crazy about US Marine stuff. They're crazy about it. So we were able to get all kinds of stuff for that. I got a British Chemi uniform at home. I got it wrapped up in a bag so it don't get, you know, it was one of the first British desert camis that came out. They were ugly. God, they were ugly. Ours were prettier, but okay. You're not interested. Okay. All right. I'm just kidding. I'm kidding. All right. Y'all need to look that up, okay? I ain't got time to look it up, and I'll try to find if we can do it. But anyway, let's graph this right quick. Graph these two. And there is one function. And there is the other. And you see that, is there much difference between, what I'm trying to say is there much difference between the exponential function as far as growth and the logarithmic function? No, there's not. You still see that right there, and you got this right here, but you don't see that big of a difference. We'll get into that later. All right. Let me get the roll. Y'all know who's here. Y'all